First, I'd like to wake you up, guys, a little. We're going to move on to the physical side. We're going to get out from the quantum world to the real world. There will be some quantum mechanics on this one, but in the real devices. How many mathematicians are here?
How many mathematicians
How
are
many
here?
physicists? Computer scientists? All right, so I have and some chemists, I can see that, physical chemists. Okay, but this is a perfect environment for a job that I learned when I got to graduate school, okay? And one of my professors was telling me, I think it was a C++ or something. And so he said, there is one professor asked a question to a bunch of people like mathematicians, computer science, and physicists in a room. Prove me that all numbers are prime, okay? Prime numbers. Everybody knows what prime numbers are? It can only divide by itself and 1, all right? So then, first mathematician started, okay? He said, I will do it with induction, said mathematician. All numbers are primes, so we're going to prove that. Mathematician said, all right, 1 is prime, 2, which is the n, by induction is the prime, n plus 1, 3 is prime, okay, everything is prime. Physicists, all right, they started. 1 is prime, okay, 2 prime, 3 is prime, 4 experimental error. Everything is prime. Lastly, the computer scientist, right? He's going to prime. He said 0 prime. Yes. Doesn't like that. 1 prime. 0 prime. In Dr. Marlowe's world, of course, it's not 0 and 1s. He's going to put all the quantum states, and there's going to be n states, but that's what it essentially is. So my computers that I'm going to talk about, the chips, is in this world. Okay, so 0 1s and 0 1s. Okay. All right. I know that the mathematicians doesn't take the 0 as a number, so that's fine. All right. So I'll start with the historical basis, and these are this work I think from 2006 to 2013, 2014. We are doing something different right now, photovoltaics and things, but it will. These people are, most of them are the students, and they are in graduate school or something. They helped us in several stages. And the blue ones are working in similar projects. They are using the some tools in different materials, but so they know that we are using the system. But this talk is not about the photovoltaics and things. It's going to be purely by the computers, computer chips. Okay. So a little history first. We're going to start. Okay. What is the next generation computers? What's the future computers? If not quantum, what's going to be what can we do with the physical system that we can have right now, all right? And then we're going to talk about, I'll explain to you if nobody is familiar, the building blocks of a chip. I'll try to explain it very simply, and then I'll note all these challenge regions, which are the materials challenge regions. We have to do something, or we have done something on these areas to move the computer progress, and then what we are doing, basically, and what are the future materials that are not working on these, but what will be the possible things in the next 10 years, 20 years, or what's happening right now. So a little history. You know this guy, Gordon Moore? How many people know that? All right. How many people know from the students, Moore's Law? So this guy, I found his original paper in 1965. He was a Fairchild semiconductor engineer. He was also the founder of Intel. And he looked like a pretty nerdy engineer. And he wrote this paper. He was given a task. All right, what's going to happen in the next 10, 15 years if we invest on this chip making business? Right? He did a cost analysis. His paper is nothing about the integration of the chips, but he did a cost analysis. He decided that this is original plot. Probably he didn't use any computer plot this thing. Maybe it's just an XY plot in logarithmic scale. But he said that by time the cost is going to decrease and the number of elements in a chip will increase. And the frequency is debatable. He gave it 24 months, 1965. Every 24 months, we're going to increase double the number of chips, the number of transistors in a chip, and decrease the cost by half, right? And it was a very good prediction, right? It worked. I mean, for years and years, it worked. In terms, number of transistors will increase by every 24 years. This number might be sometimes 18 months, 20 months, depending on how the progress, but it is working, okay? So this is Dr. Moore in 2010, talking about his big prediction, and still going at 2010. And we have now, with this scale, logarithmic scale, at that time about 1 billion and more than, and if you continue in the last years, and the predictions to 2015, 2014, we are nearing about 10 billion, 100 billion, or depending on the chips. So it is a little scattered, but it's a log plot, it is working. So the idea is, how far can we go? Can we can we do some engineering tricks, different architectures, put more chips, or are there real physical barriers that we cannot pass, or we gotta jump into something else, on computers or something. So that will be the basics of this talk. So, by the way, Moore was not an electrical engineer, not a computer scientist, not a computer engineer. He was a physical chemist, okay? And so that's I think it's an important part. He kind of talked about, he knew probably the material limits that will hit a barrier, a physical barrier, that's going to be end of the Moore's law, okay? So, but then I think it's a pretty good law, all right? It's still working. Now I think there was an article last month, they say that it's going to come to this end, okay? That's the new prediction on the Moore's law. There won't be any more swallowing the chips, putting more chips, but you have to find different ways to make the performance still higher. One of the things that we're talking about, low energy consumption and high mobility, the size would be the same, but the computers are still working in a higher performance. Okay? That was the thing. Okay, little review of that building blocks. Okay, so Tom was talking about AND gates, NOR gates, XOR gates. It's all how to combine two inputs, 0 to 1, in classical computer. And then you can combine in a very tricky ways. You can create almost anything, flashing LED lights, big computational things, supercomputers, but that's all how to connect those things with the four gates. And the best way to do is you have switches, okay? You can do with the switches, which can adjust themselves. If you give it a voltage, it is going to be on. If you take that voltage, it's going to be off. If you can find some kind of a system, you don't need this chip. And you can make a big computer, of course, it's going to be probably the size of the South Orange, can do the very small thing with the switches. So the idea, make those switches as small as possible. And that's coming with the transistor, okay? And so this device is called the CMOS device, metal oxide semiconductor CMOS device, MOSFET, is doing that. You have an input, let's say give a 1 or 0 input, you get 1 or 0 output. It's going to be either on state or off state, okay? How? This is just a semiconductor material. You have some open areas and then P-type silicon or germanium. And you have some metal, the blue regions, typical contacts. You have some oxides, the yellow regions, okay, insulators. So basically you're creating this channel between them by playing the gate voltage. If you change the gate voltage, you create a kind of you can make this state into off state, which blocks, there's no current, and then you can just play with the gate voltage again. You can have a current from source to drain, which is the on state. So that's a typical switch in atomic scale, of course. This is very small. The first transistor, again, is made in New Jersey. You know where it is made? Bell Labs in Homedale, actually. They had the first transistor on that one. And that was not like this. It was a NPN junction transistor. But this is a more advanced chip. So this is the thing that we have in the Moore's law 10 billion times of these things, 10 billion hundred. Each of them has to be connected. Of course, nobody is doing one by one. There are big processing tools to do that, but that's what the building block for chip is. Okay? So the size, the scale of this thing is given by this number, gate length. If you're talking about a 22 nanometer node, that's the industry size. Now we have chips like in your cell phones, in your computers, about 22 nanometers. That means the distance between drain and the source and the gate length. Okay? And that's the one that's going down. Okay? That's the one that's going down for years. I think I have a picture like this. And it started with micron sizes and going by doubles by half every 24 years. Now we have 22 nanometers. It's going to go down further. Okay? So what is the material problems now? If this is the thing, everything we can do, you can think that I can make this as small as possible, machine them, put 10 billion, 100 billion, trillion, that should be fine. It doesn't work like that, okay? Because silicon is come to its limits, physical limits, not engineering limits, architectural limits, some limits. So there are three regions that I'm going to discuss today. Insulator region, which is the yellow, and the semiconductor region, and then P regions, silicon-based mostly. And the third one is the conductor region, which is now in the industry using copper. It used to be aluminum, copper, but next generation will be nickel-based. So these are I will talk about why the differences of that. Okay, the CMOS is coming from, again, complementary metal oxide semiconductor, okay? So we have conductors in the regions, and we have insulators, which you don't want any kind of conduction in that gate. You just change the gate voltage here, gate voltage here. So there won't be any electron exchange from the contact to the p-type, okay? That's one insulating region. And then you have the semiconducting region. Okay, they're kind of a complementary materials, okay? What's the basic difference is the band gap, okay? These are filled with electrons here, and you see that there's no gap. Electrons can move freely to the conduction band, so that's kind of a metal, all right? So there's no resistance, without resistance, but there's no band gap that it has to go. In semiconductors, there is one, but relatively small, 1 eV, okay? So silicon is 1 eV, germanium is about that. So that means that with a little push, with a little voltage, you can make that a conducting region. So electrons, this can be conductors. But for the insulator, it's a big gap, and this gap goes like an exponential. So it goes like the barrier height that it has to go is e to the gap divided by the energy, KT, all right? So if it's a couple of electron volts, it becomes an exponential barrier, so that the insulators do not conduct, basically. Electrons cannot go to the conduction band. Okay? So every element has a different, let's say, purpose in your CMOS device. Okay. So how small is this? 22 nanometers, okay? If you still cannot make sense of it, what a nanometer, this is the physics number, mathematician's number, 1/10 million of a centimeter. A centimeter is about half an inch, okay? And you can think about the human hair, okay? So human hair is about, let's say, 50 to 100,000 nanometers. That means that you can put in your human hair, one part of hair, cross section, about 3,000, 4,000 of these devices, okay? So 3,000, 4,000 of these devices in the thickness of that. That's how small we're talking about. That's why you get the 10 billion number in that one, okay? And so the typical size of a building block is 40 nanometer. And if you still think that you don't have a sense of it, just look at your fingernail for 1 second, that's a nanometer. All right, if you multiply by the number of seconds in a week or something, you'll get the number, all right? That's what the nanometer is. Okay, and let me give you the Intel's processing. I was in the Sematech a couple of weeks ago, which is the next Silicon Valley in upstate New York. They have a beautiful fab, and they are doing not these wafers. Let me start this one. I think this is a 20 centimeter, 200 millimeter wafer, okay, the silicon wafer. Now they are going to not to 300 and 400, 300 millimeter wafers, which will be the next generation 350 millimeters. And the reason that you're doing it, you can put more chips and it's going to be more effective because this is a processed wafer, and every little block is a microchip. It's not a transistor, it's a micro. Every block has 10 billion little chips. If you can make the same system in a larger wafer, because the processing costs the same thing, you got, of course, it goes with the area square, the R square with the A, so the cost was going to go down. So that's why the next generation is going with the larger wafers. But if you go where I'm talking about that little CMOS device is this. Take one of these, all right? And so you see that each of them is a little chip connected with different, actually it's more than one chip. We're going to go inside that, okay? Now after this, all electron microscopy, of course, visible light is finishes business. We cannot see that, all right? And you see interconnects. These are the copper interconnects. We had a speaker from this a couple of months ago. He was working on the interconnects, all these things. So how to reduce the copper interconnects. They are the highways of between all the CMOS devices, okay? But we didn't reach our CMOS yet, okay? Continue on that, hopefully, all right? Here we are our chip, and here are CMOS device, okay? And the thing that I'm talking about, the gate or small thing is the insulator part, is that gate dielectric, okay? And that's with the electron microscope imaging, the silicon dioxide, which is the gate insulator part, that's the silicon, the semiconductor, that's the copper conductor type. And one of the problems before 2007 was that silicon dioxide, okay? That was a physical limit. It turned out to be, to increase the capacitance, you gotta decrease the D. We just covered this a couple of weeks ago. What's the capacitance of a parallel plate capacitor? Anybody who's taking my principles of physics? Here, Kristen, you have that. Capacitance were epsilon 0 A over D. Epsilon 0 is a constant, A is the parallel plate area, and the D is the distance. So in order to increase the capacitance, which you need for these, you can go increasing the A, which you don't want to do that because you don't want to violate the Gordon's rule. You want to make this thing smaller, not the greater. But you can also decrease the D. That's what people were doing. Shrinking, 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 and it came to be almost like 3 silicon dioxide atom thick. Okay, that's too thick, right? And below 3 silicon dioxide thick, okay, let's say chemist doesn't like these things, of course you're gonna write the silicon dioxide things, but if you do that, then this is two things about 10 angstroms, let's say about 10 angstroms, 1 nanometer, and then it loses its insulating behavior. Electrons do quantum tunneling, just pass through them. Your insulator is broken down, okay? Now you have a non-working CMOS. So this is why silicon dioxide is not going to be the future of your materials for the future programs. People decided, people knew that. I mean, these are smart engineers, physicists, chemists, they knew that for years ago, silicon dioxide will be gone, okay? So the research is what's going to be the next thing to put that, to replace that silicon dioxide. And let's go. We don't do this blindly. There is this international technology roadmap for semiconductors. It's a 15-year plan. Like the big governments make 5-year plans. This is a 15-year plan. What's going to be the problems that we're going to be facing in the next 15 years so to keep the Gordon's Moore laws continue, all right? So that was known that in, let's say, it's been changed in 2007. Probably it was when first discussed in 1990s, 1980s that silicon dioxide will be thin. It took a long time to find the correct material, correct change, and it took until 2007. IBM and Intel, with not, I mean, they didn't invent the whole thing. All the researchers working all over, it's a kind of a worldwide plan, and they decided that eventually I will be able to place it. And what was it? It was the high K material, which we worked for years, from 2003 to 2007, hafnium dioxides actually. How did they come to hafnium? Out of this many oxides, we decided that it should be hafnium dioxide instead of silicon dioxide. It wasn't easy, and actually, the guy who first proposed this hafnium dioxide is the next one is the Daryl Schwab, who was a Penn State graduate student at that time. I guess maybe he was a first year professor, but he did a simple chemistry analysis between the like in freshman chemistry or sophomore chemistry, and he found from the band gaps in the active region, hafnium is one of the candidates. Zirconium could be, a lot of things it could be, but hafnium energetically is the best match for after the silicon dioxide. And the problem with that was interface problems, okay? In my chip, you have the silicon here, and its neighbor, its sister brother, silicon dioxide. Now you're saying that take the silicon dioxide and put a very big atom, hafnium dioxide, okay? What happened to your lattice mismatch? Okay, or everything is going to be, you're trying to put a little Lego, think about the Legos, you're trying to put a big blocks into a small block with different notches and things, it's not going to work. So that was the main problems. But there are remedies. And that was one of the things that we changed it. And there are other things that the next generation will be, now you're working as a three-dimensional things. Instead of putting like that, three-dimensional FETs. But this is a plan, I think this is like put in the 2009 or 2010, there's a plan going to 2021, okay? And if you see that if these plans are working, you can look at the scaling length with time, okay? Yeah, this is going exponentially down, all right, with the year. And for example, we are in now 2013, and we are in the 22 nanometers. That means that in 2020, 2025, we're going to go under, let's say, under 16 nanometers, okay? And the other things, if there's a technological breakthrough or something, these curves are modified or sometimes delayed, but it is showing the exponential behavior, okay? And this is the breakthrough that I was talking about. So you see that silicon dioxide, and at this point there was a suggestion, and this is the 2005 roadmap. At 2005, there was the projection that it's going to be high K, and this really happened. December of 2007 and 2008, I think 2007, this has been changed to metal, okay? And it didn't finish. Now after high K, you see the gate electrode was going to be changed into metal, and we're going to go 300 nanometers things, and then the silicon region will be changed. Okay, we're going to talk about on those things, but that's one of the gate materials. Okay, so the problems are, we already talked about the region 1. We need a high K dielectric, a better insulator basically, and that's done. Silicon dioxide is replaced by hafnium oxide. They never, Intel is a very secretive company, all right? They never tell you, and people, they got input from a lot of scientists, but they have also their own engineers, and Intel has put something to hafnium dioxide. And I believe, and most of the scientists believe, it's the zirconium oxide, which makes sense to put that. So it's not just hafnium oxide, but hafnium zirconium oxide, and I'll tell you why it's the case soon. And the other thing is the region 2, dopants. These are the semiconductor regions. And if you make this transistor smaller and smaller, you want to still keep the same number of dopants, okay? So it was easy, if you have a big silicon, you can put a lot of dopants. Dopants are arsenic or boron atoms you can put to increase the conductivity.
Now you want the same number of arsenic and boron, but small silicon. What's going to happen? They got together, they clutter, okay? And it's going to be not working like a nice conductive, semiconductive material, but it's going to be deactivated itself, the turbines. So then you're going to have another breakdown for the transistor.
So the second challenge region is how to dope very high concentrations of arsenic and boron in a very shallow materials, okay? In a very, like 10 nanometer thickness, how do you put more arsenic and boron, okay? Because arsenic has one extra electron, it will give you an extra electron. Boron has one less electron than the silicon. That will be a hole, that will be an electron. These are the extra charge carriers that will use to increase that. So you can use boron and arsenic. You see that symmetry between them. And the problem is if you put too much arsenic, then you're in trouble. Region 3, okay, you change now hafnium dioxide, this thing, all right? Hafnium dioxide doesn't work with copper or aluminum. You need to find something else, another material. And so copper is gone after years of research. Now the nickel and alloys of nickel, nickel silicon, nickel 2 silicon. And the reason is they are, when you contact nickel silicon as a conducting element too, with the hafnium dioxide, the junction resistance goes down, okay? So otherwise, if you try to push the copper on hafnium dioxide, there will be a huge junction resistor. The transistor is not going to work. Okay? So if you change one small part of the transistor, you're going to play with a lot of materials. This is the material-based challenges. You want to make these things as small as possible, but every time you try to do something, there's a new problem coming up. Okay? So that's the thing. And we worked in 3 different areas with Dr. Kelty's group, with this one, and we're still working with Rory in arsenic. That's a big problem, arsenic clustering problem. I'm going to talk about some examples. How do we do that? We work with industry. Also, we do our films, and we did a lot of these films, hafnium dioxide, in our laboratory using pulse laser deposition. Okay, so we don't do the chips. Okay, but we can create silicon dioxide, put some kind of a hafnium dioxide. We did several of these. Put some hafnium zirconium dioxide, a toy model of the real material. Okay, and I know the industry has problems. For example, they want to have this hafnium dioxide, but also they want to have this hafnium dioxide on a certain phase, which is the tetragonal symmetry. Okay? That's this phase that's the most, let's say, durable for the processes that's going to go to semiconducting processes. Okay? And there's another phase, monoclinic phase, which is the natural phase of hafnium dioxide. It doesn't work because if you move to the very high temperatures, it just loses its stability. Okay? So we want to keep the hafnium dioxide with our thin film, but somehow find a way to force the hafnium dioxide to stay in this tetragonal phase. That's a non-equilibrium phase. If you get a powder of hafnium dioxide, it's going to be monoclinic. How come you make a thin film, it's not monoclinic? That's the trick, okay? By playing with the temperatures, laser energies, position methods, you can get this phase trapped. And that was one of the big things that we did with the semiconductors. And they did some films on their side. I did the analysis here. We did with our students with the films. And after years of thing, we figured out how to trap the tetragonal phase. I'm going to talk about that. And so in order to talk about a phase of the hafnium dioxide, and as thin as less than 1/10 of a micron or a couple of 100 nanometers, we need to have a nice microscope, a good tool to analyze, all right? We're not looking with a microscope to these things, but we use X-rays, how to determine the phase of this thing. And that comes in 2 ways. One, using X-ray diffraction, low intensity X-ray diffraction in our lab, just to give you a phase. But then the real job is the Brookhaven National Laboratory, the synchrotron radiation light source, how to pin down, how to see these layers and decide if it's tetragonal or monoclinic. Okay? So I'm going to talk about a little on that one. And this is the process. This is how we do it in our lab, pulse laser deposition, whatever the material. For example, if you're working on the hafnium case, we deposit hafnium dioxide. Now we're in photovoltaics. We worked in arsenic before. We worked in the nickel silicon. And then in our lab, basic structural characterization. And then we do go to Brookhaven. Okay, we do structural probing of those materials in some spectroscopies. I'm going to basically talk about. It's going to be a little technical on that, but I'm going to go fast. And then in our lab also we do electrical characterization. We look at the happening like that you created. Is this a really high K insulator? We can do that. We did lab view programming with our high K capacitors, which Michelle James projected, Sam Emery's, and we can calculate all those capacitances and things, and then correlate with the structural relations. What kind of structure is going to give me the best capacitance? What kind of structure is going to give me the best dopant value? Okay, so that's the structure versus that. Just a little analysis. This is the pulse laser deposition system we have. This is a laser, UV laser, and which gives you 248 nanometers. It's a very high-powered laser. You can get a hole in your little quarter if you just shoot it with a couple of let's say, a couple of 10 or 20 minutes. You can get a hole in a little quarter. Okay, you can go up to 100 hertz. We can heat up the chamber, and we can have the pressure or some other gases that according to deposition. And this is during the deposition, and that's related to Dr. Lopez's plasma work that we learned a lot, and that but this is a little microplasma, and we were not working with plasma. I know much more from Dr. Lopez's work that actually what we're creating is a little plasma, and as the vapor of the target material after the laser hits evaporates instantly, a couple of nanometers of the molecules from the target, which we are supposed to deposit from that, and they stick to the substrate, silicon substrate, vertically. Okay, so we shoot the laser these plumes, and that's where the film is. So we can correct, we can manipulate the thickness of that. We can put first, for example, silicon on top of silicon. We can put different things. And the idea, depositing these different films and then look at the structures, and this is if this is what you want to get in the end. Okay. So what I'll have to talk about a little X-ray process. It's going to be a little fast. Okay. If you have an isolated atom, a simple atom. Okay, the atoms are not like circular things actually. This is just a imaginary thing. The physicists like to imagine a nucleus and an electron circulating with different energy levels and orbitals. So if you send an X-ray to this atom, it's going to hit this electron. It's going to shoot up this electron. If there's any empty levels around it, it's going to make a transition to empty. But if they're all filled, and if you send enough X-ray energy, you can kick this electron out of the atom. That's a photoelectric effect. Photoelectric effect, that's the Einstein's Nobel Prize winning. Einstein gets this Nobel Prize not from general relativity, by finding or theoretically getting this photoelectric quantum effect. So there's a little irony that Einstein always rejects quantum mechanics, but he got his Nobel Prize with quantum mechanics. Okay? So that's what happens. This is an isolated atom. If there are many atoms around it, the situation is a little different. That atom is not going to be kicked out, but it's going to be bouncing back from the near neighbors. And Tom Marlowe showed a double-slit interference pattern. Remember that? The waves were interfering, getting the bright spots and low spots. Exactly what happens here is interference. Those atoms are backscattered and come back to the center atom because their neighbors are scatterers. Now we have spherical waves penetrating each other. That's an interference effect. Okay? What happens is your isolated atom will have this absorption. Your X-ray is going to be gone because it used to kick out an electron. Okay, and usually this will have X-rays going, and there's a big absorption, and then something spectral like that. If it's an isolated atom, if you have a crystal, because of that interference pattern, you still have that. There's a big absorption, but what you have is this wiggly thing. That's the interference pattern. That's the screen bright spot, dark spot that Omara was showing. That's the interference pattern. That's coming from this backscattering mechanism. So this is your absorbing atom. This is where you send the X-rays. There are the backscatters. You see the shift of the waves, the blue waves and the red waves coming. There's a little interference, and that causes that wiggling thing. That's the information. If you have means to analyze that information, then you know this structure. Okay, that's the x-axis is. Okay, so we use the absorption coefficient by changing the energy, tune the energy, shoot it there and look at the absorption coefficient, and finally from that wiggly thing we can get distance information. What's the distance between A and B? We can get coordination numbers. How many B's are surrounding A? We can get bond lengths. Okay, that's all the things. And if it is a nice crystal or it's a kind of a disordered crystal, all the B's and C's are scattered. We can get structural disorder information. That's a very sensitive tool. The problem is this wiggly thing is very small. Okay, that's why you cannot do X-rays in your lab. Okay, you need a nice, very powerful X-ray source. And where do you get that X-ray source? In a synchrotron. Okay. So the experiment is very simple. You go to a synchrotron. I'll talk about synchrotrons. They are basically X-ray sources. There's an electron circulating and creating X-rays. Okay? And then you take this X-ray, because the X-rays are all over the place, not a single energy. You pass it to a monochromator, so get the exact energy. If you want 16,200, 16,201, you use this device. Bragg scattering will give you the energies. You pass through the detector, measure the X-rays intensity, and you pass through to your sample, then put another detector. Some of them is absorbed, okay? So from the absorption to the incoming ratio, you get the absorption coefficient. So you tune the energy, you get the absorption spectrum. If there is a nice crystal background, you got this wiggly interference pattern, okay? So then you take that part, because it's a small part, you do the analysis on that part. You go from the energy to decay. This is a little technical, but we go to the momentum space from the energy. And if that's a kind of image analysis or electrical analysis called the signal analysis, there's a bunch of waves with different frequencies. This is called with different momentum, with different wave vectors. And there's you can simulate this with an equation. I'll talk about it. And then take a Fourier transform of the spectra. Now from the momentum, if you take a Fourier transform, you're going to get the real space. These are the real angstrom size differences. That will be the different distances from A to B, okay? So, for example, the location of this peak is somehow related to the A to B distance, and the size of this peak and the width of this peak is related to how many B's are surrounded and if they are ordered or disordered, if there's a thermal disorder. So you do a lot of analysis on these peaks. And the equation is pretty well set. It's a bunch of sine waves, summing sine waves. That's why the interference pattern is coming from, with different amplitudes. I of K's are the scattering factors, okay? And R is the bond length or the distance length. And delta is the phase factor, because when you hit a scatter, you get always a phase backwards. And then N is the number of atoms, coordination numbers. Okay? So the analysis, after you getting the data, you do the Fourier analysis, you get this Fourier transform data, and from that, you can tell the structure of the material. Okay? It doesn't have to be crystal structure, completely crystal. It's a local probe. So by a very thin film, you can tell what kind of a phase is that. Okay? And the probing size. Why do we use X-rays, but nothing else? Because we're talking about atomic scale, okay, angstroms. In order to see small things, we need to have a light radiation at that scale. Okay? I was just covering that in this week's lecture in principles of physics. I mean, this is why you cannot see an atom by a regular microscope. Because the visible light has 400 nanometers wavelength, which is much, much greater than the atom size. So you need to do some kind of a different thing. You can choose an electron give a really small wavelength energized electron, then you can probe that. X-rays has the right size in wavelength. So synchrotron X-rays is ideal to analyze analyzes things with the atom size, molecular size. Okay, that's why we use it, because X-ray wavelength is about a couple of angstroms, atom size is a couple of angstroms. They match perfectly. Okay, so that's why the X-rays are very good tools. And this is the whole electromagnetic spectrum. This is the region that we see, that we are biased. Our eye sensors are just 400 to 700 nanometer. There are UV, X-rays, higher energy gamma rays, particle accelerators, cosmic rays. On the other side, you've got infrared, microwaves, and then radio waves. Okay? So synchrotrons are circular laboratories. They are not particle accelerators. They are just accelerating electrons or positrons, anti-electrons, through the circles. Why do you do that? If you do accelerate an electron in a circle, that's basic physics radiation. If you have any charged particle and turn it around a circular path, circular path means there's a centripetal acceleration. It's not a no acceleration thing. Any charged particle that's accelerated will radiate. Circular path is intrinsically is a radiated path. Okay, accelerating, and the acceleration is tangential. So you create X-rays tangent to the orbit of the electrons. So what synchrotron does is first speed up electrons, put it into a ring, and the ring has magnets, turns electrons faster and faster, that's a storage ring, and you got tangent X-rays. And each tangent X-ray, you build an experimental station. That's the NSLS-1, the old one, which is going to be demolished by actually. I'm going in the NSLS-1. This is the last time it's going to be sentimental because in the first time I went to this place in 1993. I was a graduate student. Now it's gone, it's done. And the last run is, they're going to decommission by August. My last run is April, okay? But this is not the bad news. We have a new one. This is the old one. We got a new one, okay? That's the American way, isn't it? If you have a small one, you do a bigger one. We do a bigger one. And now we are competing with Chicago, and in Japan, the NSLS-2 has the photons. They have the lights. It's going to take another probably 1 year, hopefully less than 1 year, but then there will be experiments like that. Okay? That's the bigger ring. If you have a bigger ring, you have more powerful, important as X-rays. Okay? That's the third generation. NSLS-1 is the second generation. This is the third generation source. Okay? And so this is hopefully it's going to be fully operational by 2015. I went it last November. I think they finished all the offices and things. And there are some still cranes and things, but there are some people trying to do experiments. And this is 2011, and it was an amazing, I mean, of course, the huge DOE money coming to that one, but they did a marvelous job. I wasn't expecting that it's going to be finished because I know the superconducting super collider stories in Texas and things starts with good reasons, but never finishes. This was just on the money, okay? They're finishing now, okay? This is 2012, and this is the 2013. It's almost done. There's always almost grass on it, okay? They started the gardening and things, but it's not operational yet. They are trying to, they start taking the proposal for the new experiments, and it's gonna be, hopefully be operational within a year. My last run is gonna be in April, and then they're gonna decommission. So this is the circular path, the electron path. These are the tangents. You see those green boxes? Is an experimental hutch, they call it. You do your X-ray experiment, you put an X-ray beam, whatever you do it in that, you're gonna do that. And there's a smaller one, you can see, that's a UV ring. It's not X-rays, this is X-ray ring. UV ring, there's another station, okay? That's this one. And this is the picture of the, you cannot get a good picture of the X-ray ring, but this is a picture of the UV. And I will tell you, this is the circular path that you get, and these are X-ray paths, actually, tangents. And you can see some of the scientists, you can see that. And this is from the window there are tours for the high school kids, for the college kids every summer because Brookhaven was in trouble for neutron source. Has anybody followed in I was a scientist over there, there was a leak in their neutron source, nuclear leak, and it went to the groundwater. Of course, everybody went up, and now they're trying to do their best to change the public relations, so they're showing that whatever we do is not secret, everything's open, we don't have it, and they do a very good job right now. And these are some of the scientists. The only thing, I don't know, maybe Dr. Troy remembers Mike Neeby, and Mitra probably remembers Mike Neeby, and he was one of our best students. He got 2 fellowships from 2 offers, but he didn't. Now he's doing actually a computer science job. He's programming in a company in Wisconsin, Madison, to pay his debts for college and things. But I hope that he's going to come back to physics. Well, he was very good for the PhDs and things, and we'll see. And Joe Wojcik is the NIST guy. He built this film line by himself almost. Now he's doing the same thing again in the NSLS-2. And this guy is from Stanford. Okay, he came to help us. This is an Austrian, Florian Meyer. He was a postdoc at Goldstein. Now he has a patent position in Netherlands. And this is Damiano, Italian gang. So they come from Italy. There's a ITRS laboratory that we did. So we analyzed in this run arsenic actually in silicon. Okay, this is after the run. Everybody's laughing because I think it went well. All right, it is you got 4 days of beam time, 3 days. Sometimes it doesn't work well. All right, it's a big frustration, and you work all day, all night, and you don't get anything. I think this is the end of the thing. That's one of the stations that we do. We go X24A. That's the NIST, and the other one is this is the. Now I cannot wear shorts, or that they're forbidden on that one. But that was an old, this should be an old one. That's the thing, and that's the inside the hutch. And you see that there's a 2-inch wafer here. We spin in a. You gotta be very inventive in what you're doing it. So we need to spin these wafers very fast to get rid of the black peaks, so you don't make holes in the detector. And so we need to spin, and that was not available. I just used a computer fan. To spin it, and you come with the grazing gases. So that's where the X-rays are coming, hitting the sample. That's the detector. That's what you're getting out. There's also a lot of computational stuff on behind. Okay. So the idea is, one of the runs is to get the tetragonal phase of hafnium dioxide. We worked with the Sematec a lot. They did their films. We did our films. We went to Brookhaven, look at the structure, and finally we got this nice tetragonal structure settled, locked in with some kind of a specific deposition conditions. And that's the phase, okay? You see that the tetragonal, orthorhombic, and monoclinic. You see that there's a big competition between the monoclinic and tetragonal phases. So when the tetragonal is low, it's all monoclinic. Then goes from the tetragonal is going up, monoclinic goes down. And these are the PDA and the thickness of the film, 1.4 nanometer, 1.8 nanometer, 1.4 nanometer films. And we figured out if you use these 2 conditions, you got almost 96 to 99% of the tetragonal phase, which the industry wants. Okay? That was the thing. They don't want monoclinic phase, they want the tetragonal phase. How do we know? This is our Fourier transform data from the Brookhaven, and from the analysis of this 1.8 and 1.4, we know that this structure is tetragonal. This is the typical monoclinic phase. You got the double hump. If you have not a double hump, but also this one, that's showing a tetragonal. Of course, we're not doing it visually. We do a lot of XFs fits and get the calculated structures input at the fits output, and then we decide that's the case. And so they were very happy, okay? That was our first breakthrough that how come we find, and I think they changed their process. Now they are not processing 4 nanometers PDAs, but they are doing 1.8 nanometer PDA. PDA means post-deposition annealing. That's the secret part. They don't tell us how to do the annealing. They do some kind of a laser annealing things, but if they do that, I can tell them, hey, your phase is tetragonal, which is going to be used on your computer chips. Okay, then we didn't stop. We said, okay, let's try this experimentate. I know that the zirconium was Intel's thing, all right? And we did in our laboratory, put some kind of a zirconium into the films. Instead of just hafnium dioxide, you see that's the zirconium content, we just put a 0.1 molar ratio zirconium, okay? What happens when you put the zirconium, you delay this transition. Okay, look at this figure first. There's no zirconium. Now you see this big difference between this and this. This is monoclinic. This is tetragonal. Okay, there's a phase transition happening. The phase transition happening between 300 and 400 degrees. If you do the deposition, the PLD is a kind of a magic tank, all right? If you just change the temperature of the substrate, you got a different phase. So we figured out if you just put the 350 degrees, you got the tetragonal phase. If you go beyond the 400, it's going to settle at monoclinic phase. Okay? That was the thing. Now, if you put zirconium, you delay this thing. All right? You go to the 500 degrees amp. So there's a big difference. This is the tetragonal. That's the monoclinic. Okay. So you can tell, hey, 300, 100 degree difference. What's the difference? That's a big difference for them. Okay? Now they can process at 500 degrees, still get to the tetragonal phase. That's a big thing, all right? So by just putting, that's my hunch, Intel is just putting zirconium and things, make the film is a more stable, durable to the processes, okay? Okay, now when we hit a problem, all right, you can put hafnium in silicon. The next step is the aluminum, okay? Aluminum oxide. Something funny happens if you put the aluminum, all right? Aluminum is a very diffusive material, diffuses into hafnium.
Again, it kills your dielectric region, kills your capacitor. So you need to find a way to stop that diffusion. You don't want aluminum in your hafnium.
So what is the thing? This is not, we didn't do these films. They did in Sematech. We gave the idea in New York, but I asked them, okay, let's do a test, all right? If just give me different depositions with different annealing techniques, and then we're going to look at the crystal structure. I'll tell you which one is stopping the diffusion, which one is not stopping the diffusion. And the process turned out to be, if you do this annealing, so the idea is, you put the silicon dioxide, hafnium dioxide, but do not immediately put the aluminum oxide. You do some kind of a annealing, nitrogen or ammonia annealing
at this condition. Then kind of toughens against the surface and creates a block layer.
And then if you put the aluminum next, there's no diffusion. And you don't disrupt the crystal structure here at all, okay? So that was the project. And then we found again the difference between monoclinic and tetragonal, and we found that that's the process which prevents the aluminum diffusion and doesn't let the monoclinic state settle.
You still keep the state in the tetragonal, which is the warmest one, but also prevent the diffusion of aluminum. Okay?
That's it. That was the second part of the study. Okay, and then we got the percentage of monoclinic and tetragonal from all the films, and we can also tell how much is the aluminum oxide fraction on that. Okay, with Dr. Kelty's group. Okay, we work with arsenic dopants. Remember, for the arsenic region, we want more arsenic in a small material. That was the thing. It's kind of a solubility, all right? So this is the silicon. It's a very simple two-dimensional picture of the silicon. You put the arsenic atoms, which is the yellow ones, and which is an extra electron. You see this extra electron? That's a free electron. It's going all over the place. That's the gold. You want more arsenic, you get more carriers. That's what you want in that region. Now what happens if you put too much? This happens. You got a 4 arsenic get together, kick off the silicon, all right? And you got a vacancy and arsenic 4 vacancy. Why do you get the state? Because it's energetically more favorable, okay? But that's not a good state. You don't have any free electron for that. It just kills your Goldman behavior. There's no carriers. So that's not wanted. We don't want this. Or you can get silicon arsenic crystals, which is not the one. What we want is still the silicon here, nice arsenic distributed. Basically, we want to solve more arsenic in the silicon.
You want to solve more sugar in your teacup. That's what you want, okay? You put some sugar, okay, stir it, it's gone. You put some more sugar, then up to some point, you got the saturation level. So what do? If you heat it up a little, you get a supersaturated state, then quench it down, you have more arsenic in your sample, but it's still soluble, okay? That's a metastable state. You can get this thing. And if you disrupt this, you can get all the precipitations, okay? So we want to trap the arsenic in this metastable state. We don't, they do by the annealing. What I give them is the structures. So I went to Dr. Kelty's computation, all right, I know what are the possible structures, okay? All these are possible. At that first stage, just the vacancies are different. I know the activation energies. Can you calculate those structures to me by density functional theory? So I know the structures. I'm going to take my XF's data from Brookhaven. I'm going to use your structures in my fits and tell how many of those in my structure, okay? And that's what he gave to me. Now we're going to start the second phase. We're going to introduce these phases, interstitials on that one. But that turned out to be, yeah, with these different annealing conditions, we can really solve more arsenic in the silicon. Okay, this is the electrical activation. Okay, there's something crazy happens, but we can go back to the high activity, high charge carriers by doing this what is that? This LA plus 900 degree, LA means laser annealing plus 900 degree annealing. We can trap the arsenic in a highly soluble state, okay? That was the result of that study, okay? And in addition to that, we gave, at the first time, a quantitative analysis of this fractions of the arsenic. These are our calculations. Now we know that how much arsenic is active, how much is in this form. Is it arsenic 1 vacancy, 2 vacancy, 4 vacancy, or silicon arsenic? We gave all the proportions of that. That was the first quantitative information because you can see those classes with an electron microscope, but you don't know the quantity of those. That's for the second part. And finally, it's going to be short on this one. I said the contacts. The industry now uses copper. It used to be aluminum. Now copper, but copper has problems with hafnium, okay? The junction problems. It's going to be something else. And it's not going to be a pure nickel or pure thing, but alloy of nickel and nickel silicon alloy, okay? So again, there's always a favorable phase. And they ask me, is it nickel silicon or nickel silicon 2? Which one? Can you tell us? And we did the XF's analysis on that. I saw this funny feature. You see that peak is scaling with some part. And what they do is, they process their nickel silicon with different doses. At some doses, you got that feature. At some doses, you don't. And we look at that shoulder, and we did the analysis and tried to get the, what's the X contribution and 1 minus X contribution of this samples, okay? And it turned out to be, we didn't do the FD calculation on this one because very simple. It was a very robust feature that I can do my fits. And then eventually we found from the films that we got 50% nickel silicon, 48% nickel silicon 2, okay? So they know how to get those, and now I can tell them, hey, in your sample, you have this amount of nickel silicon 2. And the required phase, the desired phase is nickel silicon 2 because it gives you lowest junction resistance. Okay, now I can tell you, if you do this process, you can have this nickel silicon in 50% or 70% or 60%, and that's invaluable information to that. Okay, and that's one of the things that probably changed the material side. So we're going to change the gate directives, hafnium dioxide. Silicon arsenic is going to change, and basically I didn't tell you that one, but that silicon part is not going to be silicon. It's going to be germanium. Okay. There are some things about that. The semiconductor industry started with germanium, okay, in 1950s, 60s. Now people give up the germanium because it has too much impurities. It gets the impurities very fast. They went all silicon. For years, for decades, people use silicon. Now silicon reached the mobility limits. Even if you put more arsenic, you're not going to increase the performance of the computer. Germanium, silicon germanium,
has some kind of a higher mobility. Even if you don't increase the number of carriers, the mobility is increasing. So this is why people are going to go back to germanium. That's in the next 15 years. So in short, Moore's law can go, all right? But there will be some physical barriers that you cannot solve with engineers at all, okay? You cannot do some electrics, there will be some chemists, physicists, material scientists who has to change the nature of the material, okay? And that's, if we've done all these at organoids, it's still, we're done, okay? What is the next stage? These are all speculation up to this point. There are some basics bugs. One of them is the organic materials. Why do they use organics? Okay? Organics are flexible, adaptable, like the DNA thing, all right? In here, you process. But if you make the organic material, it will adapt itself. And you just give the perfect condition, it will be a transistor itself, all right? That's only the people are creating the organic transistors. The problem is lifetime. They don't have the inorganic lifetime. They're going to be just more very fast. So that's the one of the problems of organic materials, but that's in the future. And the second one is the graphene. How many people heard about graphene? Graphene is a carbon-based material. It's a two-dimensional material. It's a sheet of material. I'll give you a little history. Okay, it's not. Carbon is a very versatile material. It can be multiple superconductors, graphite. It can be diamonds. It can be like graphene. These are really tough materials. They're two-dimensional materials. A little history. This is what we should do in our physics SPS meetings too. Two professors, actually Andrew Graham is the professor, Kostya was the graduate student. They were doing this crazy Friday experiments. They were bringing some kind of a toys. Let's try this inside. You have to get a physics paper or something. One of the toys that is, all right, let's get a graphite and try to make it as thin as possible. How do you do that? The easiest, obvious way is scotch tape. Take a scotch tape and then another scotch tape, then get a smaller and smaller and smaller. They went almost to one-hand size because graphite has the graphene structure. It's built up. You cannot do it with other material, but on graphite. They figured out that's the graphene, and they got the Nobel Prize for that. Okay, that's a very. I think this is the fastest Nobel Prize that I ever in physics. This was a very short discovery, short while, and they got the Nobel Prize in 2010. Okay, and graphene is good for the future of the semiconductors because you can go one atom thickness. It's so tough. Okay, if you can make a transistor from the graphene, I mean, I was talking about that small thicknesses and things, 3 atoms is not good for silicon. You can go almost atom size. So that's why it's hot. Nobody has successfully made a good chip yet, but that's in the process, okay? And that's some of the wafers from the graphene. IBM is working heavily on that. And you got high electromobility, okay? Longer carrier, and it will enable higher performance. You can go as thin as one atom. You can do a one atom transistor, that's gonna change the world, okay? That's the one. Low power, it's not gonna eat a lot of battery and heat up. And planar, you can do planes, you can do two-dimensional, three-dimensional things, and compatible with the other part of materials. So it's very, very promising. People are trying to do, they didn't get the performance of the CMOS drivers, but I'm sure that in 10, 15 years, that's one of the big possibilities, right? Okay, and so here are some simple two graphene things. What you're doing is keep the silicon, put your graphene, put your contact, and continue on that, okay? And so these are our collaborations. I mentioned a couple of them. I think I'm going to stop soon. And one thing is, I just want to say that I'm originally from Turkey. I'm really saddened today that they closed the Twitter, and I hope that it's going to be just for one day. And this is, thank you for listening. That's a picture from 2008, and thank you, and teşekkürler. Okay?